Just a second. Yeah. Okay. Hello, everyone. Today we'll be talking about tournaments. Let me just define what a tournament is. A simple graph G on n vertices, well, simple directed graph, such that there is exactly one edge between any pair of vertices u comma v. So what that means is, for example, if G were 4, if I'm looking at a tournament of size 4, then I have 4 vertices. And between any two of these, there's going to be exactly one edge. And of course, the way these edges are oriented, that's what's going to determine the tournament. So you could also see tournaments as elements of 0, 1 to the n choose 2, 1 bit denoting what direction you have for each possible pair.
So then it's basically just a complete directed graph.
Yes, sure. Right. Okay. So that's the definition of a tournament. Now, tournaments satisfy a lot of properties, and just going to discuss in general whenever you have a tournament-related problem. What are some things and techniques that you should keep in mind? And we're going to just discuss a lot of interesting, cool problems related to tournaments. So perhaps this is something that many of you would be knowing. And yes, so as people have been saying, you can also treat this as take any kn and direct each edge of the kn. Therefore, you have a complete directed graph.
So you don't know which sides it's directed towards before the problem.
No, I mean, it is not really hidden in that sense. It's not similar to like sorting yesterday or something. It's just, you know that you have this graph and then some edges are flipped. So, yes, the graph must be complete. So there must be exactly one edge between any pair you call. Okay, all right. All right. So the first thing we're going to be discussing is a very curious properties that tournaments enjoy. Some of you may be knowing this. It's proof that every tournament is Hamiltonian. What does that mean? That means you can find some ordering of the vertices. So if G is a tournament on n vertices, let's say they're numbered 1 through n, then you can find the permutation of these sigma 1, sigma 2, sigma n, such that there is an edge from sigma I to sigma I plus 1 for all 1 less than or equal to I less than. Essentially, a Hamiltonian. Have any of you seen this before?
Yes.
Okay.
Yes.
So does anyone have any ideas on how we can prove this?
I mean, I remember the solution, so I can say it.
Sure, go ahead. Yeah.
So the idea is that we induct on the number of vertices in the tournament.
Right. Okay.
The base case is like obvious. So let's just assume that we have it till some n minus 1 vertices.
Okay.
So we draw the Hamiltonian path in the n minus 1 vertices, and we consider the last vertex. Let's just place it somewhere outside for now.
Right.
And in the notation in which you've drawn, if we have a directed edge from Vn minus 1 to Vn, then that completes the path.
Right.
So that can't be the case, which means the directed edge has to be from Vn to Vn minus 1.
All right.
Similarly, if there's a directed edge now from Vn minus 2 to Vn, then we have another contradiction, since we have Vn minus 2 to Vn minus 1. So similarly, all of the arrows must be from Vn to the other vertices, but now we just put Vn at the start of our path.
Okay, very good.
You could also phrase a solution with extremal principle. You consider the maximal path
right?
and assume there's something outside of it, and then you do this exact same argument.
Yes. So these are both ideas that are going to work. One was, let me just recap that for everybody. So the two solutions that were presented are we induct first on n. So the idea is induct. So for n equals 1, that would be the base case. For n equal to 1, obviously there's a path, just take that one vertex itself. And then in the inductive step, you have a path with n minus 1 vertices. And you have this vertex vn that you want to somehow fit here. And now we look at vn minus 1. If vn minus 1 maps to vn, then as was marked earlier, we can just complete the path. So we can assume that vn actually points to this. And now vn and v1. If vn points to v1, then again we're done. And so v1 points to vn. And so essentially what you have now is you have this sort of variable. So let's say if vn points to vi, we denote that with a 0. And if vn points to, and if vi points to vn, then we denote that with a 1 on the edge between the two. So can anyone tell me what this edge will be labeled?
0.
0, right? And what would this edge receive? 1. So now you have this sequence of ones and zeros depending on the state between each vn and vi, and it started off as 1 and it ended up at 0, right? So that means in between you must be able to find at least one point where it switched from being 1 to being a 0. And if you look at this place, then you'll find that here we have vi pointing to vn and vn pointing to vi plus 1, and so we can just put vn right in there. We're done. The maximal path argument runs exactly the same way. Just look at the maximal path, and if it does not contain all the vertices, then you again consider a vertex outside the path and include it as we saw. Is this clear?
Yes.
Yes.
Hamiltonian path means like a path will have all the vertices.
That's right. Yeah. Okay. Now let's move on to an interesting question based on finding this Hamiltonian path. So now imagine we're playing a game. So we're going to return to, in fact, very similar to yesterday's setup in a way, but then again, not really. So now imagine you have the tournament, and there is someone who knows the tournament. So there is, let's say, Bob again. Let's introduce Bob. Has full knowledge of the tournament, and to know things about the tournament, you can ask Bob the direction of an edge between two vertices u and v. That's one question. Now, and let's say you're tasked with actually finding this order, this sorted order, so to say. Please.
Multiple sorted orders.
Yes, there can be. That's true. So this is just a tournament. So I'm sorry, that's sure set sorted. What I mean is just any Hamiltonian path, and we're interested in finding one such Hamiltonian path. And a very natural question you could ask is, how many questions would it take? So can anyone tell me lower bounds?
N minus 1.
Sorry.
N minus.
Okay, n minus 1. We certainly don't need to ask everything on the path. That is true. Any other lower bounds?
N log n, maybe, because we know something. Okay, no, that won't work exactly. Never mind.
Okay, what about algorithms to find
Oh
the
yes,
Hamiltonian?
something like log of n factorial, which is n log n, because like every single thing you ask, it should give like roughly one bit of information, and for permutation you need like log n factorial
Well,
bit.
n log n,
Something like that.
and log n factorial is actually, I think, minimum, because we could just take the tournaments which are sortings which are orders on it. Like,
Yes,
all
okay.
orders are also tournaments. I mean, not the
So
vice
we do
versa.
have the information theoretic bound from yesterday. So you can prove that it requires at least log 2f and factorial questions simply by enforcing. Bob tells you that there are no cycles in this graph, and then there is only one Hamiltonian path, and that actually depicts a sorted order. And so now you're essentially sorting these n numbers. And we discussed that yesterday, and that takes at least n log n steps, of course, up to constants. And so we have a lower bound. But now let's not focus too much on that. Anyways, I don't want to use too much material from yesterday. How do we figure out the actual path itself in as few questions as possible? So we have some lower bound. We know that we require omega of n log n questions. How can we prove a matching upper bound?
Okay, what's omega?
A matching upper bound.
What's omega?
This just means like you require at least Cn log n questions to find the Hamiltonian path.
So it's like big O's at most as omega is at least.
Omega is at least, O is at most.
Oh.
So omega of
In
x,
theta is a mix of both.
x for some absolute c, and O of x means it's at most cx for some absolute c.
And in fact, theta of x also exists. Which is
Sorry,
theta of x is also there, which is the mix of both of them.
would mean both. That's right.
NC2 is an upper bound.
Okay, NC2 is certainly around. Just ask out everything, and then you should be able to find a path. Okay, so let's think about this algorithmically. If you did have the entire n choose 2 vertices, like n choose 2 edges, sorry, how would you go about actually finding the path? What sorts of ways do we have of finding the path?
We could do it in
We
the
just consider like a random one and start inserting.
Just
Yes,
walk
exactly.
around and
You would try
either
to
you like
replicate-
reach a cycle, in which
Yes,
case
add
you would
one
do
vertex.
something with that.
Sorry. Sorry, go on. Yeah.
I was thinking you just walk around like the graph and you either reach a cycle or you reach a path. So that might help somehow.
Okay, so there are examples of graphs where that will terminate very quickly. For example, if I construct some, okay, I mean, I can describe this explicitly. Let's say you choose some prime p congruent to say 1 mod 4, and you look at and you make a graph on p vertices. Let's say you number them from 1 to p, 0 to p minus 1, and you join I to j. Oh, sorry, p should be 3 mod 4, and you join I maps to j if I minus j is a perfect square. Mod p. So this way, there's exactly one edge in each direction, because if x is a perfect square mod p, then minus x cannot be. So this is an example of a valid argument, and here you'll find that half the edges leave and half the edges come.
Okay,
And so cycles will happen very quickly in this type of graph.
right.
Okay, so let's go back to the thing we were working. The setup was we were trying to include one vertex at a time. So let's say we currently have n minus 1 vertices, and we have this one new vertex that we're trying to insert into the sequence.
You could
And
do
what we
it
knew was
similarly
that-
to how Adit's proof was done. Like we just compare each direction until we find this thing which is like opposite directions, and then we add
So
it there.
let's revisit those labels. We have, sorry, this points this way, and this points this way. This was a 1 and this was 0. And what we're interested in finding is that consecutive 1, 0. So like there's a 1 and then it's immediately followed by a 0. That's what we're interested in finding, right?
We do a binary search.
Yes, but how do you implement it? How does it work?
Like
You
we
compare
just look at, we
something-
compare the one with the
and
middle.
let's say it's 0. Okay, what now?
Then we check on the left of that.
Exactly. Then now there must be a 1, 0 thing on this left hand, and so we can sort of half our search
Right.
space again.
Give us an n log n algorithm because we get log 1 plus log 2 till n log n.
Exactly. And so this is very similar to insertion sort from yesterday. It's that there it was more obvious that you should be able to use binary search. Here too, you can use binary search if you're very careful in this, in defining these bits 1, 0, etc., and then trying to locate this position where 1, 0 changes happen. It is very much possible. For example, let's say you get 0. It's very much possible that there is a 1, 0 change in here as well. Maybe it reaches 1 in between.
But it's
But-
possible there isn't.
It's possible there isn't, and anyway you have a guarantee that it must be there here, and so you can just work with that. In the other case, when this is 1, then you can recurse to this. So in either case, you're halving the search space each time, and so this takes log n steps in figuring out where to put this current vertex. You ask log n questions to Bob, and then if you add up over everything, you again get something like n log n plus just overfind log n.
Wouldn't there be log n and not log n factorial on the LHS in the sum?
Yes, that will be log n factorial, which is of course then n log n.
Like on the LHS, there is a factorial in the sum, which I don't think.
Yeah, it should just be log n, I think, on the left-hand side. Yeah.
Okay, so that was a very nice little detour we took. So that proves that there is an Hamiltonian path, and we can also find this Hamiltonian path almost efficiently by figuring out very few edges. So even if you have this graph, even if you don't have this graph explicitly stored somewhere, but if you can still check between two vertices, if you can check is there an edge between UV, if you can do that quickly, then you can actually find a path as well. That would be a real life benefit of this. Okay, next let's move on with some other graph theoretic facts. One thing that is very useful very often in tournament problems is the sequences of out degrees or the sequences of in degrees. Let's for now focus on the out degree sequence. So let's say you have a graph, a tournament G, on n vertices. Let's say 1, 2, all the way till n. And let us say that d plus of I denotes the out degree of I. That's the number of edges that leave vertex I. Okay. And without losing generality, let's assume that these vertices, they're labeled such that this is true.
Is that DTI?
No, that's d plus. Plus meaning it's an out degree.
Okay.
Third,
So
I
let's say
think
we have this.
is it correct to say that any sorting algorithm also works with tournaments? Because I think that if you have a sorting algorithm, it necessarily requires comparison between consecutive pairs, right?
Well, yes, if you have a sorting algorithm, then the underlying tournament is already going to be.
I mean, how will you sort a tournament using merge sort? Like, how can you divide the tournament into two and then merge it?
You can do
Yes,
all
that's
of
what
that.
I'm saying. So what I'm
Like
saying,
if you have the same algorithm like before, if you have two sequences like this, you can still implement merge sort on these, and it will give you a longer tournament. But the problem with this approach is that your sort will not be what's called a stable sort. It will come up with different orders each time, and that's simply a problem of the tournament. And it's not necessary that this will work even in all circumstances. For example, well,
can it fail?
Ips
I
would
don't
continue
think it
to
can
work,
fail.
but sorry.
Like, can you give me an example where it will fail? I don't understand how it can fail.
Well, I mean, it could end up giving you two different orders on the same exact sequence.
Right.
Yeah.
No,
Okay.
it can't give two different. Yeah, I can. Sorry.
So
what is
let's
D
say
plus again?
d plus of I is the out degree of vertex I.
Okay.
What that means is if this is I, then there's a couple of edges that leave and there's some that come in. So the count of these, that's d plus y.
I would like, how is it? Isn't the out degree say? No, okay, got it.
Sorry?
I thought the out degree is same, but actually the degree of all the vertices is same, and the out degree and in degree may be different, right?
Yes, yes. I mean, they could be same, but then they're not guaranteed to be all same. Okay. So let's say we have this sorted sequence. Now, what we would like to estimate to understand this out degree sequence better is maybe things like how large is d plus of I. This is a very useful technique, by the way, in general also, when you're trying to maybe double count things on tournaments. It's very useful to know that the out degrees satisfy some inequalities that we're going to prove now. Okay. So let's say I want to find a lower bound on d plus of I. Can anyone tell me how I could do that?
Isn't
Isn't the
isn't
lower
it
bound
one?
is 0?
Yes.
One. Yeah.
Like
If I
Ah,
is not one or if I is not one, lower bound is one.
Okay. Let's do it this way.
Oh,
Can you all tell me something
like
about
this.
d plus of 1? How small could d plus of 1 be?
It could be 0.
It could be 0. All right, acceptable. What about d plus of 2? Can that be 0?
1.
No, it has to be at least 1.
Why can't it be 0? What happens
Because
if it is?
if it is 0, then for example, d plus of 1 has to be 0, which means that all of the edges have to be outward, have to be inwards from d1, from 1,
Right?
which means that there will be an edge from 2 to 1, and that will count in the out degree.
Yeah,
So n
exactly.
minus
So
1 by 2
look
should
at
be
the
the
edge
answer.
between 1 and 2. It has to be directed in both directions at the same time, and that's obviously not
Is
happening.
the answer ceiling of n minus 1 by 2?
Yes, that's right. D plus of I is always at least I minus 1 by 2. And the way we prove this is,
By considering a graph of the first, complete
again,
graph of
I
the
guess,
first I
or
things.
induction. Does
uh,
induction work?
well, not quite.
Okay.
So let's say we look at a certain I. Now, this sum, d plus of x from 1 to I,
And
this is at
C2.
least I choose 2. Why? Because, first of all, let's say we consider this new graph where we're only looking at the first I vertices. Then certainly the out degree of each vertex in the original tournament is at least as large as the new out degrees of each vertex in this
Right.
restricted tournament.
And then the
Right.
out degrees will sum to the number of edges.
Exactly. And now these restricted out degrees just sum to the number of edges in this subgraph of the first I
Wait, I didn't
vertices.
understand. How do you get the out degrees as?
Okay, so let's say you look at I. I has a couple of things it's pointing to. Now, a few of these could be bigger than I, and a few of these could be smaller. You can sort of remove the ones that are larger than I. Let's say these are all larger than I. But in either case, the total out degree will be at least as large as the new out degree of I, which would be this. Does that make sense?
No, but how do
Okay.
you like get the out degree as greater than?
That's right. Okay. So let's say G prime is the new graph that you obtain when you only consider the first I vertices. That's still going to be a tournament because there is still an edge between every pair of vertices.
Yes.
Agree?
Yes.
Now, d plus G prime of I is at most d plus of G of I. Do you agree
Yeah,
that this?
that's correct.
Okay. So that's exactly what we're doing here. Here we write sum I, and this sum is equal to I choose 2 because it is simply counting the number of edges
Okay.
in this subprogram.
Got it now.
Okay. And now because d plus of I was the largest here, that tells us that I times d plus of I is at least as large as, and that's at least I choose 2. And so we ultimately end up proving that, one second. Sorry about that. Okay. So you get d plus of I is at least I times I minus 1 over 2I, which is just I minus 1 over 2. And of course, you can improve this to ceiling because the d plus of I is an integer. So that gives us a lower bound. Can we now also obtain an upper bound?
Yes, we can just do I minus, we can figure out the minimum in degree of I, right? And we can subtract n
So
from
we
that.
basically just flip all of the edges in the tournament.
Yeah.
And then we do the same thing.
Yeah, so we get
Okay.
n
So what bound does that get us?
n minus floor
Should
ceiling
we
of
just
n minus I minus 1 by 2.
yeah.
Yeah, that's the ceiling.
Um,
N
right, so
minus
let
ceiling. N
me
minus
just
ceiling of
specify that. Okay. So d plus of 1 is at most d plus of 2 all the way till d plus of n, right?
Yeah.
Now, note that we also then have, because d plus of I plus d minus of I is always equal to n minus 1, because every edge is connected.
so it will be n minus 1 minus n minus.
Yeah.
We will have d minus of 1 is at least so on all the way till d minus of n. And therefore, from previous argument, we can see that d plus of the ith thing from this end, which would be n minus I plus 1, this is at least as large as I minus 1 over 2 ceiling. And so that tells you d plus of n minus I plus 1 is at most n minus 1 minus ceiling of I minus 1 over 2. And now if I call this I, then I get d plus of I is at most n minus 1 minus ceiling of minus I plus 1. N plus 1 minus I minus 1 divided by 2 is equal to n minus 1 minus ceiling of n minus I 2. And just send n minus 1 in there. This becomes, well, hold on.
It will be floored. It should be floored of n plus I by 2 minus 1.
Mm. Okay, let's actually just get rid of the floors because it's really necessary. Meaningly makes our life complicated. So we have this. This will, of course, now n minus I plus 2. Sorry. Okay, that seems fine. And so we have this upper bound as well. Okay, so this
How do
actually
you-
tells you that
How do you get the lower bound as I minus 1 by 2's ceiling? Like I got IC2 till there, and then
now IC2 is I times I minus 1 over 2, and I times d plus of I is at least as large as the total sum because that's the
yeah, okay.
maximum of degree, and just divide by it. Right.
Okay.
Okay, so this lets us actually prove this nice little upper bound. And this will be useful in the problems that follow as well. Okay, so we're now going to do, of course, a C9 or a C8. I'm not sure. I think a C8. Some of you may have seen this problem before. Just
Wait, we can't see the problem if you have already.
yeah, no, I'm
Is
touching
it the one with like Alice?
Yes. So of
Okay.
course,
Oh,
now you
the
can.
4 and 1 now.
Huh.
And I forgot the question.
Okay. So now we know where the origins of Bob come from. Well, here it's the King of Hearts, but I believe he was renamed Bob at some point. Okay. So the problem basically is telling you that there is a hidden tournament. and you as a player have to figure out if there is at least one town or one vertex in this tournament that satisfies d plus of v at most 1. You want to know if this is the case. And you're allowed to ask foreign questions, and you have to just report yes or no, depending on whether there's a town I that satisfies d plus of v at most 1. All right.
So we want there to be some which has 0 or 1 outgoing roots.
Yes. Okay, so what are some strategies to actually figure if this is possible?
Try to make a subline which has lower. If you start with a city, would ask for any other city, and if it is out, go to the one it's going out from, and then go to the one it's that one is going out from, and do that again and again until you so that you
Right.
so
Okay.
that you can minimize the more stuff which goes for this.
My first thought is that we already have bounds on the degree,
Right.
on the out degree of a vertex. So maybe we just, and this might be a bit naive, but maybe we just question about one of them and we try to bound about that vertex, and maybe that gives us some information we can work with.
Okay. So the problem with these strategies is that the co-op does not have to necessarily cooperate, and whatever vertex you choose to do that strategy from, that could just be a really bad vertex. And then it's not so helpful. And so instead of doing that, we should instead try and actually force things to happen. What I mean by that is, can anyone tell me what is the maximum number of vertices that we could have that all satisfy d plus of v at most 1?
2.
2.
Are you sure about that?
No, actually,
Three,
3
right?
like a triangle.
Right. Okay. So why can't there be 4?
Because then we just have the same degree bound. So like the d plus of the fourth vertex is at
Yes.
least
If there
2.
were 4 of them that all satisfied at most 1, then at least in that sorted order, we would have that all of these are at most 1. In particular, d plus of 4 is at most 1. But at the same time, we knew that d plus 4 was at least 4 minus 1 by 2, which is greater than 1. And so
Won't it be 3?
do that.
Won't
And
it
can
be
we
2?
have a 3? Is it possible that all the first 3 are equal to 1? Is that
Yeah.
possible? Okay. How?
Like those 3 just 1. All of them have 1 each.
Okay. So what would that look like? What would it look like for these 3?
Blue.
Like a cycle.
Yeah.
Right. This would be like a triangle, and then you have a bunch of other vertices left,
And they
and
each
they
go
could all
to
just point.
A3.
So in these scenarios, you have up to 3 vertices, all of which have out degree 1. Okay. So let's now try to figure out how we can go about actually determining how many such vertices there are, if they exist at all, things like that. So let's say we question one edge and we receive this direction. What does that tell us?
that tells us that
One can have at most one other one if it cannot have anything. If it has to set.
It sort of tells us that u is most likely having out degree more than 1. It could be a fake. It could have out degree exactly 1, but then again, you probably expect it. It's practically sort of already gone. It's no longer a potential vertex that actually is going to be.
It has more chances than D.
Yes, sure. You could put it like that. It has more chances than the other vertices. So now let's say you want to question another vertex. which of these would you perhaps ask about?
V and W.
Okay, the question is right here, and question just says that you have a hidden tournament. You have to ask up to 4 edge questions, edge direction questions, and you have to check if there is one vertex, at least one vertex, without degree at most one. All right. Okay, good. Right. So now we have comes along this new vertex W. Who do we want to determine? Who do we want to ask W with?
V.
V. Why is that?
Because
Because
V
then we'll know if V is 0 or 1. Like U
Yes.
is already 1. So
Exactly. So the way to think about this is you have these variables d plus of 1. Mind you, this is not sorted because we assume that in a very specific case, this is just the arbitrary sequence of out degrees as a function of the graph that we currently know, the edges that we currently know. So initially, this is a all zero string, and what you want to determine by the end if there is an element that is at most 1. And when you query an edge, one of the vertices that you query about necessarily increases by 1, right?
yes.
Okay.
Correct.
So if you question U and V, then V necessarily increases by 1. Sorry, U necessarily increases by 1. And so every single question, you're able to sort of increase D plus by 1. When you consider W and you ask W with V, let's say, you could receive something like this, or you could receive something like this.
Okay, so it's easy to show that in at most 2n questions, we can find out whether any of them have 0.
Okay, that's a very good idea. Can you describe your strategy?
First, we just like start from U and we keep going. Whichever one has 0, we continue with that and some other random vertex.
Right.
After we're done, we'll have n by 2, which have 0. Like only we will have 0. Or like some other, we'll know that exactly one vertex has 0 at most.
Right. Okay.
And
Okay. So, yeah, go on.
no, actually.
All right. So if we look at the structures that we are obtaining here, you might notice that this is very similar to yesterday again, when we were actually trying to figure out the maximum in some sense. So we're sort of skipping steps here, just looking at a potential maximal vertex, which would be a vertex with very low out degree. It's beaten by very few people. So once you've asked this for all n vertices, what you will have is you will have this tree. By the time you've gone through your list from 1 through n and you've asked, okay, 1, 2, if 1 beats 2, okay, so if U points to V, then we say that V beats U. Let's call it this way. Hence the name tournament, actually, because if you were to host something like a tournament on n people, then the results of the match, assuming there are no draws, would look like a tournament, and you could draw an edge depending on who won. So in that sense, you're just trying to find a player who lost very few matches. And so it makes sense to keep switching to the winner. And now you're looking at 1, jump to 2, or if 1 wins against 2, then you stay at 1, and things like that. And eventually, if you just draw out the set of win edges that you know about, or the directed edges you've already asked about, they will form this tree. And here you've asked something like n minus 1 questions. And by this time, if you look at the out degree sequence, that's 0 and a bunch of 1s. And what this tells us is very interesting. It tells us that these 1s, they're practically already dead. All it takes is, so if I were to question any 2 of these 1s, for example, I could always kill out one of them.
Right.
Right?
Yes.
Okay. So
it'll take at most n more to remove all of them except 1. I think.
And
Like we just compare
right?
random ones.
It would take like
And then-
n minus 2, I think, because you only have to ask n minus 2 questions to get rid of most of them.
No, like
Right.
we'll have to ask n minus 1 by 2 plus n minus 1 by 4 plus something like that.
Okay, so one thing we need to avoid, let's number these v2 to vn minus 1, and let's say this is v. So this is sort of like a root. It is the root. and the others are numbered v1 through vn minus 1. And something you need to avoid, something that you need to be very careful about, is you don't want to question two vertices you've already questioned, because that gives you no additional information. You cannot say that you've discovered a new edge because you'd already asked that before. So you have to avoid asking edges that are adjacent. Is there a very easy way to do that? Is there a way we can actually avoid always questioning two vertices that are connected?
Yeah, we just like go in order, selecting the first pair, second pair, and then and the
Okay,
ones
well,
which like remain one still, we can again compare with the remaining ones. So we'll like
okay.
eliminate in every step.
Right. Okay. Um, let's not go down that route. Let's instead think about this as maybe you want to assign. Let's say I want you to split this set of vertices into, like, say, two groups, such that in that group I can ask questions between any two vertices, and in this group as well I can ask questions between any two vertices. Can anyone suggest a very simple way to do that?
Can you just like repeat what we're trying?
You just
So let's say this set S of vertices without degree 1 is called S. I'm asking you to split S into these two groups, S1 and S2, such that if you, maybe not you, let's call them U1 and U2. If U1 and U2 both belong to, say, one of these sets, let's say S1, then you shouldn't have queried U1, U2 as an edge earlier. So basically U1 and U2 are not connected in the tree, directly connected.
you take alternate levels of the tree.
Very good. Essentially what we're doing is we're going to bicolor the tree. And now if we were to assign them, let's say, white and red, this is red, and then this layer is just all white, and then this is red. So if you just do
You
coloring
put
of
all of the white ones in one group and red ones in the other.
exactly, except for V, of course.
Except
because
for
V is so you have
So we
this one
split
group.
the n minus 1 into two groups.
Exactly. So you have this set of red vertices and you have this set of white vertices, and you're guaranteed that when you ask questions between red and between white, you can't possibly ask the same
right.
set again, right? Okay.
I would think that you should just compare the root node with vertices we have not compared it to until you get something that either kills the root node, or we compare all of them. If we compare all of them, we are
So
done.
we'll
And-
get
And if we don't kill the root node, we have eliminated everything we have compared it to. Like if we kill the root node, we have wasted one move and not wasted one move. We have wasted one move and we have killed everything I was connected to. We kept earlier.
Okay, I think I see a
So that's
simple.
pretty efficient in eliminating stuff.
Okay, so one problem with that approach is that V could actually just be, everything could be mapping to V. And in that case,
I
you
think
can't
I
actually
see a
ask
sim-
anybody
I think I
else.
see a simpler solution.
If everything is mapped to V, then V is done, right? I mean, if everything is mapping to V, we are done. We know that V is the solution.
No, V is not the solution.
If
I mean,
everything is mapping to V.
Okay, yes.
okay, fair. Right, okay.
So we
Why
just
can
like-
we not just like again eliminate n minus 1 of the V1, V2, n minus 2 of the ones with degree 1?
Okay, how will you go about doing that?
Like we just consider pairs,
Okay.
and in every
But you do,
move,
yeah, right. So that's the problem, right? But you do need to avoid that you don't ask the same question again.
yeah, like we know what we asked right before, so
Okay. So
we
how
can
will you-
just. Okay, you mean like we might be forced to ask the same.
Yeah, exactly. So this coloring makes it a lot easier to see that, okay, you were never going to ask the same question again, which is why we introduced it in the first place.
So we could just like repeat the algorithm in S1 and then S2, and then
Yes,
remove some
We're
vertices.
just going to repeat the tree idea in S1 and in S2. So
I
the
lagged out
point
of
was
the
that
meeting.
the
I
point was
lagged
that if
out of
we
the
had a
meeting.
bunch of zeros, then we were able to convert that into 1, 1, and a bunch of zeros by repeatedly querying in this way. Oh, sorry.
I lagged
One-
out of the meeting. Could you just repeat what was done in the past 2 minutes or so?
I'm where did you leave?
I think it was while I'm not so sure precisely where.
Did you catch the bicoloring part?
No.
Okay. Did you get to the part where we started with this tuple 0 till 0, a lot of zeros, and then we made it 0 and a bunch of
Yeah,
ones?
I got that part.
Okay. So now the plan was, because you have a bunch of ones, and now any new query we make is just going to make one of them 2, and then those vertices are sort of useless in the sense that we don't care about them anymore. because they can't be potential vertices without degree at most 1. So what we want to do is sort of extinguish a lot of these vi from v1 through vn minus 1. We want to
Yeah.
remove a lot of them. So how can we go about doing that? That was the question we asked. And the idea was to split. So the point was we wanted to repeat the same algorithm as before. The point was if you have a bunch of zeros, if you do the tree idea on those zero vertices, you can bump up the out degrees of all of them, save for 1, by exactly 1. And so you reach this 0, 1, 1, 1 state. But the problem with doing that directly is that you might actually end up comparing the same edge twice. And you want to avoid that. And so we decided to split it into these two groups, such that if you ask questions between this group and questions between this group, then you can't possibly have a
Yes, I got it.
then you can't possibly have right, exactly. Okay. So now that we've bicolored, this will how many questions does it take here? Let's say this has R vertices, this is a W vertices, so in R minus 1 questions and then W minus 1 questions. We've reached this state where everything is 2 except for the root of this, and V. So we have essentially we're left with a 0, 1, 1 thing. Right?
And how many questions have we used up till now?
You tell me.
2n
N
minus
minus
3.
3 plus n minus 1, I think.
Yes, 2n minus 3. Up to 2n minus 3, 2n minus 3. It's fine to just read this as 2n. Does not matter too much, the constant error return. So now we have 0, 1, 1 and a bunch of 2s. These 2s are sort of useless. We couldn't care less. Now you have these 3 vertices. 2 of them are sort of extinguished and 1 is not. And what we would like to do is check if any of them will actually survive till the end. So can anyone give me a very simple strategy of just figuring out if any of
Just
these
check between those 3 first. Assuming you have not checked already.
Okay. Okay, so you can just check everything in between. And let's say you find that they're still 0, 1, 1. So, or maybe not 0, 1, 1 actually, because you can, well, there could be an edge between these two. And let's say there's also an edge between these two. Note that there can't be an edge between all 3 because that would mean there was a triangle in the original graph. Well,
Yes.
actually that could be, sorry. So you could have asked for these 2 and then you could also already be in a triangle. So maybe it looks something like
Why can't we just layer another tree onto the first tree? Wouldn't that be simpler? I mean, do the tree
That's not
algorithm.
necessary, like, because most of them are already waste.
Why don't we just check the 1, 1 and then we just eliminate one of them?
you can't necessarily do that because 1, 1 could have been compared before. That is why we split into 2 groups anyway. Remember that this comes from this group and this comes from this group. So there could be edges between these 2.
Okay.
Okay, so we can say like this. Between
so
those 3
we know for
themselves,
sure that only one of these could possibly work, right?
yeah.
Yes.
And if
And
I
we can
want to
easily
test
we can
one
easily
vertex,
remove one. We can easily remove one of those 3 because the sum has to be 3. So either it goes to 1, 1, 1 or 0, 1, 2.
right. If it goes to 0, 1, 2, what happens then? In one question, we have asked 2 and minus 2 questions, and
So
we
then
now
we individually check with all the remaining ones.
exactly, we can just individually check, and this takes n questions, this takes n questions, and that's 4n. But there's of course the unfortunate circumstance where you have a death triangle, and you have this 1, 1, 1 situation, and you're just stuck in this.
But now in this case, we know a lot about the graph in that all of the other vertices have to be pointing towards all 3 of these, right?
No, that is false. We do not know that. We just know a bunch of trees.
Oh,
We couldn't possibly know too many edges, right? Because
Right.
we've asked a linear number of edges. So you
okay,
can't
that's
really-
fair enough.
Yeah. So we've asked something like 2n questions, and now we have these 3 potential candidates. And it seems like to check them, we simply have to just check the entire graph.
But I will take
Right.
3 and
Well, not 3, like just one vertex and with the rest of the graph. And so that takes something like 3n, and so we have a 5n strategy. And we somehow want to reduce this. We want to somehow save n queries somewhere. So let's revisit our algorithm. Where are we being wasteful?
so you use the first n to generate a graph, and then you use the next n to.
Like our trees are separate. Why can't we combine them?
Okay. We separated the trees. Well, not really. I think the tree separation is a good idea because you're able to sort of reduce it to very few candidates by using still only n queries. So that is not where the problem is. I think the problem is already in our very first step that we did. The first step we did was we actually removed the 0 from the picture, from the equation. And I think a few people were saying this at the time, that we should continue comparing V with the other people. And this is what we're going to be doing now.
Yeah, we should
We
do it so
somehow-
that we can get V has one kingy at the very, or V is checkmatability and we're done. Because if V has one kingy, then we can just start efficiently removing stuff by just comparing stuff with one kingy.
Well, no, you
Okay.
could still end up in like a death triangle, in the sense that you could still have everything just reach out one. So you're not safe from that. Okay, anyway, so let's do it this way. We've asked n questions, and so far we have this one vertex and we have these two sets. We have S0 and we have S1, and we have vertex V. And we know that all of these have out degree one, but there are no edges in between. So this is an independent set. This is an independent set. And V maybe has edges to a few of these, maybe some from, well, only from S0, really. Can't have from S1, for example, because we've, actually, let me just call this red and white so that it's clear.
Wait, we can have like to S1 also, right?
No, because V is also part of the tree. So,
Okay, yes. Correct.
yeah. So now imagine we have V and V is 0. What happens when we ask V with a white vertex? So we know that there is no edge between these two, so we couldn't have possibly queried this.
So we just do it instead with those, we do it with V.
Okay, so what happens when we query V with a white vertex?
We also know like whether V has any more edges or not.
Okay, that is
So
true.
we can save more edges.
Well, okay, so let's do this a little more formally. Let's say you have a white vertex W and you query V and W, and you find that W points to. What does that tell us?
That means V is
W-
still 0 and W is 2. So W is removed.
Right, so W has now reached 2, and so W is no longer a potential candidate. So we've sort of eliminated W, and V still has out degree 0. And let's say we continue asking white questions this way until we reach the point where W points to. So you've eliminated a few of these maybe. And now you have V as, let's say, 1. There is some vertex W that V pointed to. How should we adapt our strategy?
What if we like swap W and V?
Okay. So what do you do next?
So like you put like W in V's position and you put V in the whites. Or can we do that?
We can't do that because we need to ensure there's no edges, right? That's the condition that these sets satisfy.
Right, but how do we know that in the beginning when we started querying, I mean, 0 with like all the whites, like it's possible that we had already queried one of the whites with 0, so we might be querying it.
We couldn't have done that. We couldn't have done this, right? Because they're the same color. So there's no edges
Okay,
between.
okay, yes.
Yeah.
Okay, so like if we get V to be 1, 2, then we can start checking like between them.
Okay. Let's think about it this way. If, let's say, I told you that V is not a candidate. V cannot be the final answer. Are we done then?
Sorry?
Let's say I told you that V is not an answer. So like V does not, you don't need to worry about.
Yeah, then we're done because we just check the other.
Exactly, then we're done.
Because you can check the
V
other
has
two.
to be a candidate.
Right. So the idea is to look at V. So remember, you already have this coloring S1 and S2, right? So keep that. Let's say S1 is the set of red vertices. This is a set of white vertices. And you have vertex V, which has out degree 0. And you have a couple of these. And V was maybe already asked with a couple of vertices from red. Anyways, S is going to contain all the vertices you did not ask about V with. All right. Does that make sense?
Okay.
Okay. Now keep asking V with all of the vertices in this set S that you have not already asked. So essentially, we're trying to extinguish V. And the idea is while you're extinguishing V, if V does not get extinguished, then something else does. So to put that more clearly, when you have V and W, if V points to W, then it's fine, then V is safe. But in the other scenario, we find that actually W can now be eliminated. So you can actually delete W from whatever set there was here. So let's do this carefully. We've asked n questions so far. Remember, we've not asked any questions yet, and now we're going to begin our asking. So we're going to take V and we're going to look at S. S has some size, and let's say we make Q questions. So we question.
Wait,
V
but
with,
S could contain both red and white vertices.
yes, S can contain both red and white vertices. That's completely fine. I'm not mandating that S is the set of white or the set of red vertices. This is the set of vertices about which I don't know the direction of V with. Note that for the other ones, I know this direction. So whatever set I have left over, they all point to V because V has out degrees here. So I'm going to look at a W here, and I'm going to question V with everybody basically until there comes a moment when V is eliminated. What do I mean by V is eliminated? V becomes 1. V becomes 2. Sorry, V has out degree 2. All right. So let's say I ask Q questions up to this point. All right. So far I have asked n minus 1 questions. Fine. Let's say I ask Q questions. So, and V is eliminated because it has out degree 2 now. All right.
Wait, I didn't get you. So what did we do?
I'll ask the direction between V and every single vertex in this set S that I don't already know about. I know the others because all of them point to V. And I keep asking V with this until V has out degree 2. And I know it's certainly not going to be anything useful.
Okay. Yes.
Okay, so let's say this takes Q questions. All right.
Sure.
Okay. Now, at the end of these Q questions, this could also just be like the full thing, or maybe I discover that V in fact is a. Okay, so one scenario is that I do all of this and I find that V has out degree at most 2. Sorry, at most 1. So V is not eliminated. All right. What happens in that case? In that case, I already know V is a vertex that works, right? So I'm done in like 2 n questions. If V not
Sure.
eliminated. And therefore, I can assume that there is a moment where V reaches out degree 2 and I have to like stop. So let's say that happens after Q questions and I've questioned what is W1, W2, WQ with V. All of these were probably just V pointing to those, sorry, Wi pointing to V, except for 2 vertices. So let's say that's Wi and, well, of course, the final vertex as well, because that was the moment when this happened. Everything else points the other way, right?
Yes.
So how many vertices is this?
Q minus 2.
Q minus 2, right? And these can never potentially show up again.
Yes. They are
So
done.
I remove them from their corresponding S1 and S2 sets. All right.
Okay.
Sure.
And now let's say this has the new set side. Let's say the new set is S1 prime and S2 prime. So I've removed those faulty vertices. All right.
Okay.
Okay. And now I have this one vertex Wi left and this one vertex WQ left. And of course, I let these be wherever they were. All right.
Yes.
So what can you tell me about this? What's that equal to?
Q minus 2 again.
Q minus 2. And what's this?
Like the original stuff, so n minus 1.
N minus 1. And so what's this?
N minus Q
N minus Q
N
plus 1.
plus 1. Yeah.
N minus Q plus 1. And how many questions was I asking each time I was just exposing? Okay, anyways, let me not jump steps. So we know certainly V is not it, right?
Yes.
And so the only potential vertices that could work are the ones left in S1 prime and the ones left in S2 prime,
Yes.
right?
Correct.
And I know that there's no edges between vertices of S1 prime and I know there's no edges between vertices of S2 prime because of the coloring argument.
Yes.
And now with mod S1 prime minus 1 or cardinality of S1 prime minus 1 questions, I can reduce S1 prime to one potential vertex. That could be it. Because remember, all of these already have out degree 1.
Yes.
Because we built that original tree back then. And so in n minus q plus 1 minus 2 vertices, which is n minus q minus 1 questions. There's a couple of subtle cases where s1 prime is equal to 0 or something like that, but let's not get into that. Those are details that can be handled. So in n minus q minus 1 questions, we're able to reduce to 2 vertices, after
Yes.
which we win in how many questions?
Uh,
2n questions, right? Just ask this with everybody else.
yeah.
So this is 2n questions. Here we have n minus q minus 1.
And we
How
have
many questions did
n,
we ask earlier? We had asked
n
n
also.
minus 1 originally, and q questions over here.
Yes.
Fine.
So Q cancels out.
Total sum is less than 4, less than or equal to 4.
Oh, wow.
And so on. The important part is that these two cancel, and they cancel because each time I was supposedly wasting asking information about V, I was actually removing vertices from S1 and S2.
Right.
I was also at the same time reducing my size. And so you sort of save questions there. The point is, when you would have reached that death triangle state, you would have to ask about V with everyone else anyway, right? So the point is just ask that beforehand. And because you're now asking beforehand, you already have early information that some of the vertices in the tree, they already don't work. So I don't actually need to bother with them when I do the red-white short. And so I sort of use V to get information along the way as well while eliminating. And that of course solves the problem. All right, so any questions? I'll just stop because this was a long problem. Well, no, not long, but maybe it had a lot of key ideas and a lot of steps. Any questions?
Wait, so each time we queried V with the like set, whatever, set of non-asked questions, like non-asked edges, like we could either remove V or we could remove like one of S. So we didn't waste any steps, so as to say.
Exactly. That's the point. And in fact, it can be proven that you require at least 4n minus O of log n questions, always, like no matter what. And in fact, the solution is very similar to binomial trees that we discussed yesterday. So feel free to explore that a little. So you can actually show that 4n is pretty tight, up to, in fact, logarithmic additive errors. Okay, cool. So we can now move on from that problem. So that's another theme you'll notice very often today, that there is this tournament and we're actually going to try to find things that we know to be true from maybe some inductive arguments. But we're going to actually also try to find them using as few questions or as few edges as possible. Okay, now let's move on to another very interesting property that tournaments satisfy or enjoy, and that is every tournament G has a king. Or what's a king? A king is a vertex U such that there is a directed path of length at most 2 from every vertex to U. What in if we revisit the if we say U maps to V means V beats U, then that means that either U beat U. Okay, that sounded very horrible. But the point is, if either
Wait,
vertex,
I solved the question in a kind of different way, and I got like we can have at most like one or two left,
1 or 2 what?
like one or two moves left.
Do you mean like by the end?
Yeah.
Yeah, I mean, again, don't get into that. I think you can like be very, very, like precise about this, and you can get something like 4n minus 7. That's not the point of the problem. I imagine if in the actual contest you proved something like, okay, this wasn't on a contest, but if you did prove like 4n plus 10, let's say on an actual contest, I doubt they would like be very harsh on you and just deduct a lot of marks for no reason. So like, don't worry about that.
Okay.
Okay, so every tournament G has a king, and a king, of course, like I said, is a vertex V, I'm going to call it now. Such that for every vertex W, either V beat W
Could we
or
prove this with induction? Like,
X that then beat W.
could we prove this with induction? Like, if you have n vertices, say you take the king, and then you consider another vertex. So we can you just scroll
What's
up
the
to
king
like,
defined as again?
Sorry.
What is the king defined as?
So the king is defined as a king is a vertex such that,
So it can be reached from every other vertex.
yes, in at most two, such that there is a directed path from U to V with less than or equal to 2 edges for all vertices U in the tournament.
So
And we're trying to prove that every tournament is a king. This is a very interesting result. It's sort of telling you that tournaments are very, like every vertex can reach some specific special vertex very quickly.
okay, I
so
think I
if
have
we
a
have a
solution.
guy who beats at least n plus 1 by 2 people, then we are done, right?
Why are you done?
Because I mean n plus 1 by 2 double, n plus 3 by no, yeah, n plus 3 by 2. Because then that guy beat n by 2 people, n plus 3 by 2 people, and one of those people, at most one of those people beat 0 people. And the remaining people, it might have just been cycles. So, you know.
Wait, induction will work, I think, yeah. You can classify them into sets of people, like people who reach in like 1 step and people who reach in like 2 steps.
Okay.
And then we take the king as well in that graph, I guess.
Yeah, and then when you're adding the new vertex, you decide, let's say that vertex points to you, the previous king, then you can add it to class 1. If it doesn't point to the king, then say it points to some vertex in class 1, then you can add it to class 2. Otherwise, both the king and all vertices in class 1 would point to our new thing. So you could put the previous king in class 1 and that new vertex as the king.
Okay.
But what about
And
the
that's
class 2 people?
Sorry.
What about the class 2 people?
The class people are already just pointing to the new king.
the class 2 people are already pointing to the class 1 people.
Okay. So I see a lot of solutions that are being discussed.
Okay, and I think I have another one idea which I'm not so sure how. I think it should work. You consider the vertex with the maximum in degree, and intuitively that should be the king of the graph, if not the king.
Okay, all very promising ideas. And I'm going to present two solutions to this. Both of them already are in the air. Let me just go with in order. Let's first do the induction solution. So the induction solution proceeds by adding one vertex at a time. And let's say that you have this vertex V. Let's say we take some vertex U, remove it. Now there's a king in the resulting graph, right? So you have these class 1 vertices. And then you have these class 2 vertices. And now comes along this new vertex U, and U wants to also potentially be doing something. Now, if U points to V, then everything is fine. You can just add U in here and you're happy, right? And you already have a king for your original graph as well. Otherwise, if U points to some vertex here, then you can just add U to class 2, right? And you're still done. And therefore, what you've obtained now is that U maps to V and maps to all of these as well, right? What comes next?
No, those should map to you, right?
Sorry. Yeah, good.
Now you make that vertex the new king, I guess.
Exactly. Now you make you the new king because it sort of like stole V's immediate
Now
kingdom.
we have a revolution.
Exactly. So you can sort of change U to V and you can push V down to class 1. And then you find that U is the new. Cool. Was that solution clear? Any questions? Let me just read chat.
No question.
Okay. And now again, as people were saying, the degree, the vertex with maximum in degree, that's the other solution. So there are again these two ideas. You find that these two ideas are, just while like they appear practically everywhere in graph theory, inducting and looking at things that are maximal in some sense, and both of them produce solutions here. If you think about it, whenever a vertex U was not working or not happy with a certain king, it actually V was a subordinate to U, and all of V subordinates were also subordinates to U. And so we look for a vertex U that has maximum in degree. Let's say we do that. Say U has the largest in degree in the graph. All right. So you can again define class 1 and class 2. But the problem is maybe there are vertices outside of class 1 and class 2. So just to be precise, class 1 is a set of vertices that point to U. Set of vertices that have one edge pointing to U. Class 2 is a set of vertices not in class 1 that have some edge pointing to some vertex of class 1. That's class 2. And now maybe there's a vertex outside of this. So maybe let's say W is a vertex that is outside of this class 1, class 2. There could be multiple more. There could be W1, W2, but let's just focus on one such vertex. Now, if this vertex W is not part of this structure, then first of all, W cannot point to U. So U points to W, right? Secondly, W can't point to any vertex in class 1, because if it did, then of course you would just push W into class 2. So all of these also point to W. The exact same thing
So
is
we just continue increasing the number of.
not continue increasing. You already chose the one that has the maximum degree. So this can't happen. There can't be such a vertex.
Yeah.
So like if U has in degree D minus of U, then you find that D minus of W is at least as large as D minus of U plus 1. And that's a contradiction because you'd already chosen the one with maximum article. Can we have 3 classes? Well, no. In this case, you can't have 3 classes because if there were a class not belonging to class 1 and class 2, then it would have a larger in degree, but that's not possible because we chose U with maximum article. U.
But
Yes.
like, is it possible to be 2 kings or something?
Yes, certainly. It is possible for there to be 2 kings.
Is it guaranteed for 2 kings? Like in non-trivial cases?
Yes, in most cases, you will be able to find 2 kings. But the arguments there are actually very difficult. I mean, not impossibly difficult, but they are quite tricky compared to what we've so far discussed.
Okay.
Okay, so this proves that I can find a king in every tournament, right?
So, is this the solution for C8 only? I just left for some time.
Sorry.
Is this like you're just doing the solution for C8 or you're doing something else?
No. We solved C8 here.
Okay.
This line here to denote that it's over.
Can we have 3 classes in the induction proof?
Well, I mean, whatever would be the use of the third class. Our eventual goal is to prove that everything belongs to class 1 or class 2. And then you have this new vertex W and you just prove that, yeah, if it's not in class 1 or class 2, then it has a larger in degree, but that's not possible.
Okay.
All right. Now we're going to be discussing some very interesting questions, and that is finding a king in the same setup as before. Now you're asking questions about the tournament and you want to find a king quickly. All right.
One slow algorithm would be to do it inductively, but that will take O of n squared time.
Exactly. So one option is just get the tournament and then do this process that we were doing so far. That will give you some
Yeah.
like
Or
O
we
of n
can
squared.
just like find all the vertices with n degree greater than d, like n minus 1 by 2, gif of n minus 1 by 2, and check those.
Why n minus 1 by 2 specifically? Also, how will you determine all the vertices with that larger in degree or odd
No,
degree?
like the maximum degree, right? Oh, okay, yeah.
Yeah, so like to actually figure out the maximum out degree vertex. So in fact, we know that to find the maximum out degree vertex, I'm not sure if we know it this or not, but we do not, at least we do not have any algorithm that does it faster than n squared. Now, I don't know if that is because it's impossible or if they haven't found anything yet. I think it's because it's impossible. My memory fails me
But it
here.
would be
Wait, wouldn't
intuitive.
we just
that
need
it-
SC2? Why n
Sorry.
squared?
I
No,
mean, of course, we're only interested in up to constants, right? And what is n choose to, but n squared with a
Yeah.
half at the start.
no,
Yeah.
intuitively it makes sense that it can't be done below O n square time, finding the maximal out degree vertex.
Yes,
So
because
you have
because sort
to
of like
vary lots of edges
yeah, exactly.
going
Yeah.
out of each vertex.
So I think I yeah, my
Like,
memory fails me. I do not remember. Okay, I think because it's close to 6. Okay, you guys can just present your ideas. I think we'll start a discussion on this. Okay, so there are two types of solutions we're interested in, let's say, or two types of models that we're interested in exploring. The first is a let's be simple about it for now. Let's say first I allow randomization. So you can present algorithms that are random in some sense. So randomized algorithms, okay.
feels like we should be able to like devise an algorithm to find, the maximum degree, in degree or out degree or whatever. Because if we find one which is greater than n minus 1 by 2, then that will have to be the maximum, right? Actually, no, never mind.
So essentially, now we're interested in answering two questions. A randomized algorithm would be interested in the average complexity of your algorithm, whereas in a deterministic setting, we would be interested in what's the worst case complexity of your algorithm. And we're going to try to devise algorithms that do really well in both of these cases for some definition of really well. We don't really know what's best possible yet. So, yeah.
I ring meaning the full cycle.
Right?
By ring you mean a full cycle, right?
By
Full cycle.
full cycle.
I misread king for ring. I thought you were saying
Can you speak up louder, maybe?
nothing. I just misread ring.
I think
we do
O
the
of n
inductive thing?
square is guaranteed to work.
Wait,
Yes, of course. We do have
I
open square
just
for both.
realized something.
That's just a trivial algorithm. Just
We
question everything.
managed to find an algorithm that can find all kings of a graph within less than O of n squared time. Then we can find an efficient algorithm to find the maximal out degree.
You want to find all edges of the graph.
No, all kings of the graph in, let's say, less than O of n squared time. Then you can use that algorithm to find the vertex with maximal degree. So there should be something.
So how do you do that? How do you use all kings to determine if
Like if you have all kings, we know that the vertex of maximal out degree is sum of the kings. So we can check through all of the kings to see.
But what if there are many kings?
so actually I think I'm not sure about this, but I think there are graphs where like 99% of the vertices are kings.
Oh,
So
okay.
that would not be a very good
Yeah,
strategy at all.
like the
Yeah.
first class to be very small and then the second class just too big.
Yeah.
Or we could do the graph you're describing before, which is very balanced in P equals to
Yeah,
3 mod
exactly, because
4.
everything points to everything. Yeah, so there would be probably many kings in that graph. Exactly. Yeah.
Yeah.
How fast is the inductive algorithm?
How fast is the inductive algorithm? So like, I mean,
You don't need to check class 2.
but maybe
N
maybe
root n-ish.
maybe everything is in class 1.
Yes.
And that would become n squared.
But wait, won't the inductive algorithm also be more than n squared? Then?
I mean, how will it be more than n squared? You are certainly asking up to n vertices each time. Why would you ask more than that? And I mean, also like you wouldn't want to repeat edges. Maybe the algorithm we're thinking of is repeating some edges. You don't actually need to do that. You
Okay.
like no algorithm, if it's being smart in that aspect that you don't ask a single edge twice, it can never make more than n choose to queries. So yeah. So O of n square is basically just like
So what is the best case, like if we had god luck algorithm, what would be the, how much would we have to check?
sorry,
What's the best case? Like what is the answer for if we had a god luck algorithm?
a deterministic algorithm. Well, I
God's luck
would
algorithm. Like if you had a god's luck algorithm, which somehow, what's the minimum required for proof of king? It's
for
n.
two kings, like
For a king, we require proof n, right? We need n checks to figure out if something is a king for certain.
I mean, it's not always necessary you have two kings, right?
I'm saying if you have a king, there are necessary
Yeah,
n checks, right?
it is right. Yeah, sorry, go on.
If you have a king, you need to check n kings for certain, right?
If you have a king, you need to check n things for certain.
Be sure that's a king,
Okay.
right?
Yes.
And you said like we can have 99.99% kings kings.
Yeah, probably.
Right.
I
So
don't know if it's 99.99%, but you can certainly ensure like a positive proportion of them being kings.
okay, so why can't we just have like all of those kings into n checks? So like n square checks.
But that's still n squared, right? And also,
Yeah,
how are you
exactly.
figuring out this list of kings beforehand?
Yeah, I'm saying
And,
like even
and
if you have
remember, we're
god's
not
luck,
interested in the maximum out degree vertex. That's a really hard problem. What we're interested in just is finding a king. So if you have a list of kings, then I've already solved it. Okay. I think like we'll take a break once it's 6, and then we'll rejoin at 6:30, and then I'll discuss algorithms that do both of these. In the meantime, present any ideas that you guys have.
how
Uh,
does
so
anybody
the
know
six-
how
the
minimum how many need
6:30
to
class will be a continuation of this.
Yes, that's right. Yeah.
does anybody know how many we need to know for certain that we have covered all the kings? Like how much do we need to prove that we have gotten all the kings? Um, um, do we need just one king or do we need all the kings?
Just one king. Find a king.
Okay.
Wait, so we could just like start with the random vertex and like start walking in a direction. And then once our walk crosses 3, then we just check the first vertex we started and then check with the original vertex. I mean, the vertex where it becomes greater than 3.
Okay,
Yeah.
so think about it this way. Like whenever you guys are presenting ideas, tell me this. So there is like you're in a state where you don't know that there's a king, and then there's going to be a state when you have a potential king. Where in your algorithm is that transition happening? Where are you crossing the sea?
Okay.
So can you tell me that? Can you point out the exact point where your random walk is able to tell you that this is a king or this is not a king, this is likely to be a king, etc. There should be some point like that.
So let us just start with a certain vertex, assume it is the king, and so we'll try to prove it's the king. So we just check all of its class ones and class twos. We make a graph, a tree like that. Or a
Okay,
tree
so
that's
by the way, just to let you know, in this case, it might take you something like
n moves.
no, it'll take you more than that, right? Because if imagine I tell you this, and I give you something of size n by 2, and this is what all of it points to, and then the leftover n by 2 things, they don't behave very well. They pretend to be working for a very long time, and then it suddenly falls apart in the last vertex. So this way you end up asking quadratic.
Hmm. So let us just start with making a tree first.
Let us start with
Making a tree.
a tree. Okay.
Okay.
So again, just to let you know, a tree has huge depth. So in fact, you're being very wasteful about all those edges that you know, because you know that it's not going to really help you because these edges, will traverse a long distance. You are looking
Yes.
for something that is short.
Low depth. You can use the previous algorithm that we got for the previous question. If you try to make a depth tree which has very low depth, or at least the kind of small depth which we were doing greedy algorithm for depth minimization per se.
Okay, how do you want to do the greedy algorithm?
Like for every step we just take a node, we compare it with the node which we have not compared with any of the previous nodes, right? And we can just take the node which has least things which are going to it as the node, as the new node of the tree, like the main thing. What do you call the main thing? Root, right? So we can just compare the root of the previous tree to any other node and just make the winner the new root.
Well, okay, but how is that like? Where does it become a king though? Because I mean, if you're checking whether the root of that tree is a king,
It won't be a king with high chance, but
right?
we can just look at look at the stuff which is within. No, that's not working. Ah, that's not working. Sorry.
Okay. I think Pranav is back. So, are you there, Pranav?
Yeah.
Okay, so we'll take a short break here for like 30 minutes, and we'll meet again at 6:30, and then we'll discuss solutions to both of these. How we can find the
I'll
king.
stop recording as well. Okay.